I guess the record is started now.
Sure. You will pause it now. I think we have some folks still waiting.
Okay. Good morning, everybody. So, as you all know, it's going to be a revisit for the MetaWatch app discussed earlier by Parth. So let's get started. Okay. So let's see what's the motivation for doing the timestamping. Okay. So when we have two hosts talking to each other in a network, and we would like to know the time it takes to get processed in the network, or to know the latency, we need a timestamping device to tap the traffic from the host at this place, and the traffic will be sent to the network as usual. And again, once the packet get past the network, so again we will be making a tap here and sending the feed to the timestamping device. So here we will be doing timestamping for this traffic and also for this traffic, and we will be sending it to a capture device, which do the analytics. So this device is gonna calculate the time it took for the packet to pass through the network. So likewise, we can calculate the latency for even a cable which connects between the host, and that's how it works, and that's what we need the timestamping for. Okay, so let's see what MetaWatch or MetaMaker is doing here. Okay, so now we know that the timestamping for the timestamping we need a tap thing, and we got to do a timestamping in here. So this MetaMaker device is capable of doing doing tap, and it can do the timestamping, and also it can aggregate the traffic and funnel it to a application device here. So okay, so it can do this thing with the time frame of just 5 nanoseconds. Like it can both replicate the packet to a outbound port and also to a MetaWatch application. And MetaWatch is going to do the timestamping and send it to the capture device. Okay, so let's see what are the devices where we can enable the MetaWatch. So for that, the best way to do it is look for the code names where we have the detailed list of the devices which support the MetaWatch. For now, the K series and L series support the MetaWatch. Okay. So let's see the architecture of how it works, and also let's see how we can deal with buffering and oversubscription. Okay. So let's imagine we have a traffic coming in through ET1 interface here, and we'll be feeding it to the application port of a MetaWatch. That's here. So here we have a 40 KB of buffering, so that the traffic can be stored for a moment, and then we have also 8 or 16 GB of buffer at the egress point. So in the middle, we will be doing all the timestamping. But timestamps are captured at this point. When the first byte of the traffic hits the application port, the timestamp is captured for that packet. and that's how it works. Okay. And let's see the features we have. Like, we can do rate limiting of the traffic at the egress point. That's the aggregated output here, this point. So we have two options here. We can either rate limit using a bandwidth command. So what it does is, so it can, when you execute the bandwidth Mbps 1, it's gonna rate limit the outbound traffic to 1 Mbps. So while doing this, we got to be careful because we might face inbound drops as these buffers are getting filled. Okay. So next option we have is packet rate limiting. So here we can do rate limiting based on the number of packets. Like, let's say packet rate PPS, packets per second, to 298. Okay, so it's gonna send 298 packets out of the egress port per second. So that's how we can do the rate limiting. And also one more thing to note here is we got to be careful with the tab ports and tool ports. So the thing is that we have few modes which have a tool capacity of 10 gig out and a tab capacity of 10 gig. So it's going to be like we'll be having multiple tab ports and one tool port, right? So if we are sending the traffic through all the tab ports, so at one point of time it's gonna fill out all the buffer and it's gonna drop traffic. So it's always better to be it's always a good practice to see whether we are doing the oversubscribing thing. Okay. So okay, let's get started on how to install the app. Okay. In latest MOS versions, we can see the app shipped along, but if for some reason the app is not installed, or we would like to install to a particular version, so we can always go and check in the show version output. Here we can see the applications installed. So for now, in this output, we could able to see that only netconf app has been installed and there is no MetaWatch app. So let's see how we can do that. So the first thing we can do is like downloading the app from our software website and putting it to the home/admin directory. So so if you put the RPM file to this home/admin directory, and we can go inside the meta 7130 and we can do install app file, and we can call for that RPM. Then after it's getting installed, it's gonna go inside this directory, inside the RPM directory inside the flash. Here we can find it. So after any install, it's always a good practice to log out of the device and log in, because sometimes it might not show up in the show version. So we have had past cases which had the same issue. So logging out and logging in has to solve the issue. Like it shows up in the applications installed. And also, once the MetaWatch app goes to the show version output, there is no guarantee that it's going to work. So it's always a good practice to check our software downloads page where it says the compatible MOS version, where we are trying to install this watch. It's like when we try to install a MetaWatch version which is not compatible to this MOS version, it's still gonna get installed. And when we try to turn on the app, it's not going to work and it's going to throw up some error. Okay, so let's see how to turn on the app. Okay, so before that, we have one more show command to check the apps installed in the MetaMago device. That's show app. So here we can see the apps installed. So MetaWatch, MetaMux, and NetConf has been installed here, as you see. Okay, so there is a problem in here when discussing about this thing. You can see that both MetaMux and MetaWatch has been installed to this 7130. Well, if we are trying to enable one app, it's always a good practice to turn off the other one. Because actually I tried to turn on both the apps and I was able to see the FPGA got confused and it programmed both, as you see here. Like I'll show you. Yeah. So after installing the app, we can see the tab ports and tool ports here. So as using the command show interface app all description. So here we can see that for the application ports until 56, it has programmed the mux. And from AP 57 to 60, it has programmed the watch app. So it's always good to check this app, whether customer are trying to turn on both the app at the same time. So it's not going to work this way. Why it's not going to work is like because we have only one FPGA in the L series and K series device. So to check the number of FPGA we have in this device, we can use this command, like show FPGA, and it's going to show how many FPGAs we have here. For currently, we have only one. I guess we have plans to have more. Okay. Then coming to the MetaWatch mode configuration. Okay, to configure the modes, we got to check what are the modes supported by the particular MetaWatch version, and it depends on the series we are in. So execute list modes command under the app MetaWatch, and we can see the modes supported by this device. So for L series, we have 4 supported modes, that 4 into 12, 3 into 12, 4 into 12, and 4 into 12 gateway, and 2 into 12 plus 2 into 12. So this description is like self-explanatory. So while enabling the 4 into 12, it's going to create 4 cores of 12 inputs at 10G into one 10G output. So it's like this. $10G in, and it's going to get aggregated, and it's going to be 10G out. So like this, we will be creating 4 such thing. So that's how it means. And also when you see this star here, it's going to say as the default mode which has been configured. So it's like after getting inside the app using the app MetaWatch command, and you do no shutdown, by default this mode will get selected and it will be programmed under the FPGA. Okay. Next, coming to multi-core aggregation. Okay, let's see. Here, as discussed earlier, we have 4 such cores programmed by the FPGA. So we should be having 4 analytics device to work on the traffic we are sending it out. Let's say if you have only one analytics device connected to the MetaWatch 7130 device, so we can always do this multi-core aggregation, like under the MetaWatch app, execute output aggregation, and we'll be seeing all the traffic getting out of the first core output. Yeah. And all the core outputs like this one and the other one will be idle, and it not going to be used. So it's like there is always a possibility that someone might have added this output aggregation and trying to capture traffic from this core here, and we won't be seeing any traffic out. So it's always good practice to check on this thing. Okay, and to default the configuration, you can always do the no output aggregation, and you execute the show output aggregation command to check that it's going to show as displayed. Disabled. Then coming to the time source thing for the MetaWatch. So the way the MetaWatch works is, I'm going to draw a little block diagram to explain that. So when there is an inbound traffic at the application port, it's gonna capture the timestamp here. So to capture the timestamp, we got to maintain a timestamp counter. Okay. For the timestamp counter, we got to provide accurate time synchronization so that it's going to be precise. To feed the timestamp counter, we got to configure two things in the MetaWatch app. First thing is time source, and the second one is TS clock source. So in this time source, we have four options. One is, for 5 options actually: auto, free run, PPS, PTP, and system. So the default time source configuration is PTP. And even when we try to set it to auto, again, PTP is going to get selected. And let's try it out. As you can see, I've tried to configure time source as auto, and I have executed no shut. So here we can see this is a typical thing happening on the device. So it's gonna try to program the FPGA, and after that, this daemon is gonna get started. What is this daemon? This daemon is called as watchd. So this daemon is responsible for synchronizing the time feed from this time source to this timestamp counter. So as you can see here, it throws an error, like the PTP is not configured and the daemon running is timed out. So it says us that the PTP is the default one and it's not enabled, or it's not getting synchronized. Okay. So let's see about the PTP in the later page, and let's try it out with the time source free run. If we choose the time source free run, it's gonna initialize with a rough time of day, and it's gonna run freely. It's like it's not advisable for the production. However, we have a use case for this thing. Like when you would like to check on the internal module accuracy and stability, we can always use this free run to check whether the MetaWatch performs it right. Then coming to time source system, when you enable time source system, it's again gonna get synced by either NTP or PTP. So it's like in Arista devices, we cannot sync the system clock with PTP, but here in 7130 we can do that. So let's see how the PTP sync works with MetaWatch app. So there are two phases it's gonna do when it tries to sync the PTP. So there is an internal clock module for PTP. So, it's dedicated for PTP. It's called as PTP hardware clock. So it's gonna get synced from the PTP master in the network, and from here the watch D is gonna take the feed and fill out the timestamp counter. So that's is the way we are getting synced to this timestamp counter. Okay, so let's see what are the logs we can see when PTP is not configured. So here we can see that it shows as PTP is down, and the watch D says that PTP is not configured, and it raises an exception. So in this way, it may or may not work, because we have an option that when we enable PTP and it's not working, it's always going to fall back to system clock. Okay, so then we have a few show commands to check the PTP status, MetaWatch status, and if you execute the show time source command under app MetaWatch, it's going to display as default time source is PTP when nothing is being configured. Okay, and also now we know that the PTP is down. Okay, let's turn it on and let's see whether how it gets synced. Okay, to turn it on, so we got to go to the global configuration mode, and we can execute the PTP slave management interface one. The management interface one is the IP interface which has been configured in the 7130. So why slave? So as for now in 7130, we can put the device only to slave mode. We cannot put it to master mode, or it won't get elected as master by default. So we can you should always put it to slave mode. And once you change things on the time source or anything related to the MetaWatch, it's always a good practice to shut and no shut the app, so that it will be taken care of by the watch D. So this is an example of a good PTP sync. So as you all know, after the sync, it's gonna feed the PHC, that is a PTP hardware clock, and eventually the watch D is going to take feed from there and fill out the timestamp counter, and from where the timestamping, like it's from where we capture the timestamp for each and every packets which is getting inside the app port. Okay, so what's the next thing we have? The next time source option we have is PPS, which is pulse per second. So it's like a signal which will be raising abruptly at the start of the second, and it's going to drop down. So like that, it's going to be for every second, it's going to be like this. This is how it works. So the pulse length is going to be of 200 ms, and the problem with this PPS is it cannot work alone, because it tells us about the start of the second, the time when the second starts, but it does not discuss about the absolute time. So always we need some other absolute clock to get synchronized. So it can work along with either PTP or NTP. So it's like when you enable time source PPS, and when PTP is configured, the watch D is gonna take feed from PPS plus the PTP hardware clock and sends the feed to timestamp counter. When PPS is enabled with NTP, the NTP is synchronized with the system clock, So the watch D is gonna take feed from both and again fill it to the timestamp counter. Okay, so to check the time source, we have this command, show time source, and we can see that the PPS has been configured. And this command here, the show sync source, is gonna tell us from where we are syncing the PPS, like from where we are getting the PPS feed. So the default one is front panel. Sometimes we can see external too. That's in older MetaWatch versions. We can see it as external. So who's gonna send us the PPS signal? So let's discuss about it. Here is a topology where we have two 7130 devices, and we are getting feed from Mainberg time server. So this guy is the PPS source. So this guy is gonna generate a pulse for each and every second, and it reaches here. Here we could see that we have two 7130, and we have only one connection to Mainberg time server, and this guy here is not connected directly to the time server. So how it's gonna work? So this type of connection is called as daisy chaining, and here, so this master is gonna send the PPS signal received here out of this thing. So it's like there is no special configuration needed to send out the PPS signal out of the external ports. So it works automatically. So that's how this guy gets the feed, and he uses the PPS and system clock to get synchronized, and eventually the work is done. And the thing is, we have one more problem here. PPS tells us about the start of the second, and it drops, right? So there might be some cable delay introduced here. Here we can see that there is a 2-meter cable which has been connected between the master and slave. So how to calibrate that one? So we have one command to do that. The sync source front panel cable delay -8. So it's going to be like for each for 1 meter, it's going to introduce a delay of 4 nanoseconds. It's a calculated value. So we can for a 2-meter cable, we can always use sync source front panel cable delay -8, so that this the cable delay introduced by this cable is compensated here. So and we will be in right sync with the Mainberg time server. Okay. So let's now we know that we are syncing to the time source, right? And how to check that whether we are syncing it right or not. So we have a command called show MetaWatch status. So it's taken care by the watch D. Here we can see I have enabled NTP plus PPS. So what happens here is I have a good sync for the NTP. So the NTP is good, looks good. And while checking the show MetaWatch status, we were able to see this thing. So here we can see the samples. So the thing is, for each PPS pulse we receive, the MetaWatch is gonna do one. The watch D daemon is gonna do one update. Since PPS happens for every second, so for 1 minute it's gonna be 60 pulses. So there will be 60 updates as you see here, and for 1 hour it's gonna be 3600 updates. So the sync seems to be like pretty good, and we receive all the syncs, all the PPS as expected. Let's see another case where the PPS signal is is not received as expected. Here we can see that for last 1 minute, I have seen only 6 updates from watch T. So it's going to be a problem here. So why only 6 updates? It's like for each PPS pulse, the watch T is going to do 1 update. For rest of the time, it's going to be like sleeping. So it's not going to do any updates. So that's the reason for last 1 minute, we have received only 6 pulses, and it has updated 6 times. And these feeds are like, which tells us that whether we are behind the reference clock or ahead of the reference clock when we try to sync with the MetaWatch counter clock. So this is kind of example of a bad sync. And also we will be able to see these logs inside the show login output. So here the PPS signal seems to be resumed and was down for like 500 seconds. So this gives us an insight of like whether we are receiving the PPS right or not. Okay, so the next thing is going to be TS clock source. So as we discussed earlier, so this TX clock source is it's going to be the source of the base frequency of the timestamp counter. So it's like from let's say from PHC, that is PTP hardware clock, I'm syncing the timestamp counter. Okay, now I'm in sync with that, but who's gonna tell me to count each and every second? So that thing is gonna be done by this clock source. So it provides a base frequency. It's like for each and every second, it's gonna send a pulse so that the timestamp counter will be like counting each and every second as per the sync we received from the PHE. So it works. So we have few options of configuring the TS clock source here. So, but without configuring anything, so this onboard OCXO is gonna get selected. Why it is? So we have few options like crystal oscillator and OCXO. The reason why OCXOs get selected is like again, OCXO is a type of crystal oscillator, but in crystal oscillator there is an issue with when the temperature it exceeds the room temperature, it's going to be it's going to drift the frequency it's going to send. So what happens is we will be eventually we will be seeing like we will be missing or we will be behind like 5 seconds per day. So that's the reason we will be using this oven control oscillator. So this is like temperature, which it will be having a temperature sensor, and it works good with the temperature thing, and that's the reason the MetaWatch selected the OCXO as the default thing. And apart from this, we have another option like rubidium clock. So I guess we don't have that support in few series. So if rubidium clock is there, we can enable that. It's far better than this OCXO. Okay, so on this is the way to configure the TS clock source. It's I've tried to enable crystal to change it. Okay, so then let's come to timestamping thing. So for all the MetaWatch apps which we installed in 7130s, we will be seeing the same timestamp format appended at same timestamp format trailer added to each packet which is passing through the MetaWatch app. So the format is firstly we're going to see the original FCS, and then this seconds, it's UTC time, and we have a nanosecond field, so it's gonna like it's gonna be more precise. Then we have flags, then device ID. So the device ID is useful to figure out like from the packet was traversing through which 7130 device. For each 7130 device, there is a unique device ID. So we will discuss about it later. And then we have port ID. For each application port, the packet inputs or ingresses. So we will be it will be having a port ID. So using that port ID, we can figure out like from which port and from which port the device, which port the packet was entering into the 7130 device. And also the new FCS is calculated because it's like sometimes there might be use cases like the 7130 device output port, that is the aggregation port, is connected to another switch, and the packet is routed towards the capture device or the analytics device. So in that case, we still need a valid FCS, otherwise the packet would be dropped. So that's the reason we are calculating the new FCS after adding this trailer to the data packet we have. So this and this original FCS belongs to this data packet. And in flags, we'll be having a bit which tells us whether this original FCS is valid or not. And here we can see again the same description of what we discussed with this thing. Okay, and okay. So in Arista, while we do the timestamping thing, we need the keyframes to be sent along with the timestamped packets, because the timestamp in Arista, it's gonna tell us only this nanosecond thing, that is 32-bit, and we need a absolute time to figure out the entire time, so that the analytic device can use that and figure out the time difference. But in case of Metamako, like we will be sending both here, like the seconds and nanoseconds, the whole 64-bit, so that so we don't need the keyframes anymore in this. And the device ID and port ID. So here is the command to check the device ID, the show device ID under the app MetaWatch. Things to notice here is like the many commands which belong to the MetaWatch app or can be executed only under the app MetaWatch configuration mode. Okay, so and this is to check the device ID, and this command is to check the source ID. Like it's pretty simple. Like for input application port 45, it's gonna put the source ID as 45. So it's pretty straightforward. Okay, and also we have some optional extensions for this MetaWatch. We can always add the VLAN tags to the data packets in the position of the .1 queue. So it's like we can add up to 2 VLAN tags. As you all know, the VLAN tags can be used by another switch to determine the VLAN, and also in application in the analytics device, we can configure it in a way that to segregate the packets, we can always use the VLAN tags. So this is a command to enable the VLAN tag. So interface app 9. So this is the ingress port of the data packet, and the VLAN is 456. And to add 2 VLAN tag, we can always use this thing. So it's like, so the second VLAN tag is going to be the inner tag, and the first VLAN tag is going to be visible for the switch which is next to the 7130 device. So, and to disable the VLAN tag, we can use this command like interface app star no VLAN to disable that thing. And we can verify using this command again, show interface, show VLAN application ports. Okay, and also we have another option like packet sequencing number. So this seems to be a pretty useful thing. Like when you enable the sequence number for the ingress ports, I mean the application port, so it's going to add the sequence number for each and every packet which is sent out by the MetaWatch. So we can always figure out like what are the packets are dropped if we see some discontinuous sequence numbers in the packets. And to check that, show sequence number application. So it's going to show us like I've enabled the sequence number for only application 9, and it shows up here like sequence number, and it's enabled. And we can always disable using this command, interface application no sequence number. Okay, so we have discussed about this earlier. Like the timestamp is captured when the first byte, it's the application port, input application port. So and the MetaWatch adds the timestamp and it sends out through the output port. So here, what about the delay we have between? Let's say this is the input app port, and let's say this is the panel port, that is Ethernet interface. Let's say the data is coming from here to here. What about the time difference here? So how to compensate that thing? So for that we have actually by default the MetaWatch calculates those things and uses that while adding the timestamp counters. So to check that command, to check the calculated offset by the MetaWatch, so we can use this command, show interface AP9. So this is AP9, and we can see that it's like it's gonna add 0.54 nanosecond while capturing the timestamp for that application for that application board. So can we do modification for that? We have a way to do that. Here we can use this command, interface application port calibration offset 32. So we can add here, it's like using this command we can check that what all the things I have configured, and it shows up here. For AP9 I've added 32 nanoseconds as offset, and after executing this 32 and we go back and check the raw calculated offset, so it's gonna add this 32 to this 54 and it's going to show up as like this. So this tells us that the timestamp counter is going to be like plus 32 nanoseconds. Offset is plus 32 nanoseconds. So the thing is, we don't need to do this thing unless we have a use case like, but sometimes 7130 devices are like separated by long distance from the source, so that we can add some, so that we can calculate a offset and add it to it. And from few past cases, we had a bug, watch 792 in MetaWatch, where it didn't calculate the calibration offset right. So I was configuring this thing to make it right, and I guess it would be fixed in the next MetaWatch version. So they are in works on it. Okay, so let's see how to check whether the traffic comes in inside the 7130, gets the timestamp added, and egresses out. Okay, so here I'm using the same topology as used by Parth last week. So we have a 7130 device in between, and my this SN412 is going to be my traffic generator. So here I'm using ET9 interface. Okay, so and the traffic from SN412, it's ET9 of the 7130, and internally ET9 is connected to app 45 port, and ET9 is also connected to ET4. And app 45 does the timestamping and egresses out of AP 57, and finally it egresses out of ET10 interface here, and it reaches CO 137. And also I'm trying to tap a traffic and send it to SQ394. So it's like I'm sending a traffic from SN412 to SQ393, but I wanna do timestamping for these packets. So I'm tapping it to the MetaWatch app and doing the timestamping thing and sending it out to CO137. So here it's a switch, but in production it will be kind of like analytics device. So let's check whether the traffic ingresses or not. So before that, as I explained here, we can always check the connections using this command, the show interface source. So as I said, ET4 takes the source from ET9, and AP45 takes the source from ET9. That's this one. And AP57, sorry, ET10 takes the source from AP57. And also for the capturing reasons, I've taken one more output from AP57 and feed it to the management interface 5. Okay, let's see the flow. Okay, so on WCC M48 is a 7130 device. So on this, I'm checking the show interface ET9 counters, that is here, whether the packet is coming in or not. So here I can see that the packet is coming in. And now check on the now let's check on the next step, whether the packet goes to this guy and it's sent out through this guy. So for that, we can use a command called show watch counters. Again, it should be used under the app MetaWatch. So you cannot execute this in the global configuration or the privilege mode. So it has to be executed here. And we see that the AP45 is receiving traffic and AP57 is sending out the traffic. Problem with this thing is like we cannot clear this counter like using clear counters command. We cannot clear this counters. The only way to clear this is to do no shut in the app MetaWatch, and again it's going to be like it's hard for us to do that. But we have one more option to figure out here. We can use show watch counters so that we can watch like whether it is incrementing or not, unfortunately. Then let's check whether the traffic is going out of ET4 and ET10. There is one more option, like show interface ET4 tells us that I'm sending out the traffic through this interface, and the good thing about this command is like we can also see the source. Like we won't get confused. Like if you have doubts like from where it is coming, we can always check it here. And through ET10 now, that's the timestamped packets is getting out through ET10 to CO137. So that's here. We are sending out through ET10. So this is the flow and how it works. Okay, now coming to now we know that the traffic is sent out of the device as expected, but we don't know whether the MetaWatch did its work right, like doing the timestamping and things. So for that, we can do a PCAP capture. For that, I should, as I said earlier, so I'm configuring a management interface and sourcing it from AP57. So the thing with 7130 is the TCP dumps can be captured only on ETX and MAX ports. So there is no way to capture it on the application ports. So that's the reason I'm using management ports so that I can write it to a PCAP file. So to start a PCAP capture, so this is a command: start capture port MA5 destination PCAP file, and it's the PCAP file. And we can after a few seconds we can stop the capture, and we can go over here. We can find that capture PCAP file under / directory. Okay, and we can use the latest Wireshark to verify whether we did the timestamping or not. So this is the traffic I generated from that SN412, and we could able to see the timestamp added to it. And also you all know that I have configured the VLAN tag, so it shows up here. So it's like, why we need PCAP capture to prove this thing. The reason is we have two known issues from past cases. Like when the customer is trying to capture the traffic on the server side, like once the traffic egresses out of the 7130 on the server side, and he was able to see some weird issue, like for few packets the metawatch trailer was missing. So this is due to the LRO which has been enabled on the server NIC. So what it does is it aggregates multiple incoming packet, takes the header of the first packet and puts it to it and send it to the CPU. So it's like to reduce the CPU load, it does this thing. So, and this LRO is enabled in many server NIC cards, especially for solar flare NIC cards. So that's when the customer was trying to do a PCAP on the server side, he was able to see the missing metawatch trailer. So this LRO is like it's pretty random on like which trailers would be preserved, and while resegmenting and writing it to the PCAP file, we don't know like whether we are going to get the metawatch trailers or not. So so the thing is, workaround for us is we can disable the LRO on the Ethernet interface, and then we can see the metawatch trailers on all the packets received by the server. So that's the reason I was telling that it's always a good practice to take a PCAP capture on the on the 7130 itself, because it's very unlikely that the metawatch misses the timestamp trailers. And we have one more known issue where the customer was able to see able to see that the packets, timestamped packets, are not in order when it's received on the server side. So for this issue, again it's an issue with the issue on the server side. So where the receiver NIC having the multiple direct memory access queues to the multiple CPU cores, once it gets processed over there, and the final interleaving, and when we are writing it to the PCAP, so it's going to be like it goes out of order. So that's the reason. That's one more reason we always want to do a capture in the MetaMicro device itself. Okay. Then yeah, and these things, like if we see a packet, if you see a stream of packets from one input application port to a output application port, let's see, output application port, in between it get timestamped. So it will be in order always. So MetaWatch does it in order. So there won't be any out of order thing inside when it sends out through AP57, because it's like it processes like the first in first out kind of thing. Then when you expect, if we have two input application port and aggregating it to AP57, here we can see out of order thing while doing the capture here itself, because it's like they are coming from two application port, and it's pretty obvious that it may go out of order. Okay. Then finally coming to a telemetry feature in the MetaWatch. So if you configure this management telemetry and the telemetry viewer under that, and you use this to search it in your browser, we will be getting it here. So I will quickly show that thing to you guys. 1 second. Okay, are you guys able to see my Chrome? Hello?
Yeah, Vignesh, we can see your calendar. Yeah, we can see the.
So when you execute this thing, like 172, okay, telemetry. So it takes us to this thing. So it's kind of like the telemetry feed, and when you open this thing, so we are able to see the CPU usage, disk used, and memory bytes, and everything like system load and total processes. So the pretty good thing about this is like we can set it past 30 days. So we'll be having so it's going to plot the graph for past 30 days, and we can figure out the memory usage and other things historically. So this is going to be like pretty useful when we have high memory load cases, and when the CPU processors are high, we can always figure it out like when that issue started. So and also we can set it to kind of 1 second. We can set it to like 1 year. And it's going to plot the graph for 1 year. So I guess it's going to be like pretty useful when we are in handling such a kind of cases. So that's about it. Any questions so far?
Nothing from our side, Vignesh.
Okay. So if there are no more questions, we can end the session.
Okay. But yeah, thanks, Vignesh. This was very well presented. Thank you.
Thank you.
Thank you.
Thank you. Thanks everybody.
Thank you.